Hello, today we'll be reviewing the F equals to MA 2025 problem 12. The problem reads as follows. A 50-gram piece of clay is thrown horizontally with a velocity of 20 meters per second, striking the bob of a stationary pendulum with length L equals to 1 meters and a bob mass of 200 grams. Upon impact, the clay sticks to the pendulum weight and the pendulum starts to swing. What is the maximum change in the angle of the pendulum? Okay. So this problem will require use of the law of conservation of momentum, law of conservation of energy, and some basic concepts that you need to know about work and energy equations. So let's dive into this problem and see how to solve. Okay, so in this diagram, I have highlighted three different states on which the bob and the mass are moving. So this is the before state, before the small piece of clay hits the bob. This is the during state, as soon as the collision happens. And this is the after state, when the newly formed shape is now swinging upward, and the angle that we want to find is theta, expressed here. So before the collision, we can apply the law of conservation of momentum. But in this case, unlike some of the cases we've seen before, this is an inelastic collision. What does this mean? This means that no energy is lost though. So our original mass consists of 50 grams times its speed, which is 20 meters per second as given in the question. Meanwhile, the other mass's momentum is nothing but zero since it's in a rest position. Meanwhile, this is equal to, when the collision happens, it's the same as 250 grams times the velocity at which it starts moving, after which when these two masses become one shared mass. And this new velocity would end up becoming 4 meters per second, as expressed here. Now, we want to, however, find at what angle is the pendulum swinging after the velocity is now put on this new, larger formed mass. What did we do? We apply the law of conservation of energy on this new rigid body. As we can see here, the original velocity is v, so we can apply the kinetic energy equation, and that would be half times its mass, which is 250 grams, times 4 squared, because 4 is the magnitude of the velocity vector. And meanwhile, this is equal to the mass times the gravitational constant, which in this case will be approximating to about 10 meters per second. I haven't noted that here, but yeah, times the height. And by solving this, we get the height is equal to 0.8 meters. If the height is equal to 0.8 meters, that means that the remaining height that we need to find the cosine of the angle with respect to should be equal to 1 minus h over 1. So cosine theta equals to 1 minus h over 1, but since h is already given as 0.8 meters from the law of conservation of energy, we can find that cosine theta is nothing but 1/5, and theta is nothing but the cosine inverse of 1/5, giving us the answer. However, you're probably wondering that why was the energy conserved when the mass was moving upward? Like, what if there was some loss in energy? Well, I'll show you here that there was probably no loss in energy. Well, in this free body diagram, we can see that there are only really two different forces acting upon the rigid body when it is swinging. One is the tension that is pulling it towards the hinge on which the pendulum is swinging, and the other is the weight of the pendulum, expressed as mg. So what we want to do is we want to find the amount of work that these forces are doing to bring the pendulum upward. Well, since the tension and the direction of the velocity vector, is perpendicular, it shouldn't be doing any work, right? Because work is nothing but equal to force dot distance, and the distance is directed. And in this case, the distance is going exactly perpendicular to the tension variable, as the tensile force is always going to be perpendicular to this tangent force since it's radial. So therefore, this tension is doing no work. So the gravity is doing all of the work. And if you do all the calculations, which I will show in a different video, you will see that indeed this gravity is going to be causing a force that will end up maintaining this energy equation, and indeed the energy equation will still apply in this case, which means that our original answer that we've gotten here, theta equals the cosine inverse of 1/5, is indeed the correct answer. Thank you.